Recording in progress.
Hello all and welcome to the second part of the presentation. Here is the demonstration. Now we are in the basement in the laboratory. In the screen I have pinned for everyone, you can see the Rijke-tube. And in my screen you can see the output or the display screen for the experiment that we have created on control desk. In order to start this, I am first going to show everyone around the laboratory using my my phone. Just give me a moment. Apologies for that. Okay, so as I have said before, here is the Rijke-tube. First, this is the microphone that I was talking to you about, the lavalier microphone, which is going to allow us to obtain the pressure measurements from the Rijke-tube. Then here we have the coil, which is going to be the heating element for this experiment. And finally, here we have the speaker, which is going to be the actuator that we're going to use to modulate the pressure oscillations inside of the Rijke-tube. In order to control the position of the coil, we have a set of pulleys that we use with a motor, which we're going to be using in order to control the vertical position of the coil. Here now you are seeing the preamplifier that we're using for the microphone and the amplifier used for the speaker, which are going to amplify the electrical signals sent to and received from the system. And finally, here is the Escalexio digital controller, which we're going to use in order to implement RCAC. Finally, here you see the variac, which we are going to use to supply energy to the coil. Here you can see markings in blue and markings in black. The markings in blue mark the voltage levels for other tests that we were performing before. We will be performing tests on 75 volts and 95 volts today. And finally, here we have the switch, which will allow us to send an electrical energy to the coil. Now we will proceed with the tests. Hello again. Now we'll proceed with the first static test. Before that, allow me to show you what each of these graphs mean. First, we're going to have the microphone outputs. Here we have the voltage of the microphone and the equivalent pascals of the microphone. Oh, yeah, sorry, just decrease the audio. Thank you. Okay, so here is the we call it a slow because this is going to be sampled at 1000 hertz. That's the sampling rate of the RCAC controller. Here we're going to have the microphone pressure measurements using 20 kilohertz. This is just for observation purposes and is not being used in any sort of control modulations. Here in the lower left, in the middle left part, we're going to have the speaker signals that are being sent towards the speakers. And finally, here we have the RCAC theta coefficients, which are the controller coefficients that RCAC is going to change in real time. Here at the bottom, we have the frequency responses of both the measured microphone signals and the signals that are being outputted to the speakers. Finally, we have the buttons for the RCAC control. When the controller is enabled, this light will turn to green. And when attention is disabled, this light will turn to red, and vice versa. And finally, here we have the experiment hyperparameters. RU and P naught. Throughout all of these experiments, we'll use the same variables. Okay, now we'll get it started. In order for you to better hear the experiment, we'll be passing around one microphone at the start of each test so that we can better capture the pressure oscillations. So without further ado, we'll proceed with the first test, which is a static test with the coil placed at 0.4 meters above the tube bottom and supplying 75 volts of voltage RMS power. That was the end of the first test. This was the easiest of all the tests. As you have seen, RCAC basically just used a very small power signal in the speaker and was able to suppress the oscillation that we measured here. As you may have noticed, when the oscillations were forming, the FFT in this graph was the first one to notice it, even when we couldn't hear it. And here you see the difference between both sampling rates. While in here you see a smoother curve due to the 20 kilohertz that we're using in this, for these measurements. Here you can see a more choppy waveform, which this is exactly what RCAC is seeing, and RCAC is using as information in order to suppress the oscillations. Now, finally here you see the coefficients evolving in time, searching for an appropriate set of control coefficients in order to tune out these oscillations. Now then, since we are a bit far away from the 0.3 sweet spot, this took a couple of seconds to suppress. We'll see that this time increases as we go into the more complicated cases. So without further ado, now we will proceed with the second test, in which we will increase the supplied voltage to 95 volts RMS. as you saw, just by increasing the supplied voltage, RCAC had a harder time of, in suppressing these oscillations, or at the very least, it took much longer. And also, you can perceive here that the oscillations in that we saw were slightly different.
Actually, I just filled out the I-9 form, but for the onboarding, it says that
hello?
here.
Moving on. In spite of the different conditions, we were able to change, RCAC was able to converge to a set of parameters that managed to stabilize the oscillation. I should note that RCAC has no previous model information. It just is enabled and tries to figure out what the best way of suppressing the oscillations is. Okay. Now, while we were discussing this, John, thank you for your assistance, lowered the coil to a point closer to a fourth of the length of the tube from the bottom. Actually, we're exactly at a fourth of the length of the tube. The tube has a length of 1.2 meters, and right now the coil is at 0.3 meters from the lower side of the tube, which implies that we all see that oscillations are going to be more easily formed, are going to be harder to control for RCAC. So without further ado, we'll just start the next test. In this case, the oscillations were different from the position at the higher coil position. However, RCAC still managed to quite swiftly figure out a set of parameters that were suitable for this application. However, this is in a case with lower voltage supplied. Now we'll supply 95 volts and you'll see a significant change in RCAC response. So as you saw in the last test, RCAC had to take more time in order to figure out the final set of controller coefficients that would enable us to suppress the oscillations. But just like in the other three cases, RCAC was able to reach a set of coefficients that would enable us to suppress these oscillations. I just want to mention something here. At the very end of the in here, you can see the oscillations coming back. This is because by that point we have disabled RCAC. That means that without RCAC, the oscillations are going to come back almost immediately. Which means that even after there is no no noise being heard, the pressure oscillations will come back up without any control. Okay, now that's it for the static case tests. Now we'll perform an auto-tuning test. In this auto-tuning test, we will show that RCAC can reach a static controller that can be used for further testing without the need of any further adaptation. Now, without further ado, we'll initiate that test. So as I mentioned before, once we reach the stabilization of the oscillations, we disabled the adaptation and we kept the controller coefficient static. Then we disabled the controller, and immediately after, the oscillations came back. However, once we enabled the controller, the digital controller with the static coefficients was able to control the oscillations, meaning that RCAC reached a set of coefficients that could be used for later tests without any need of further adaptation. Now for the next test, we'll do a dynamic test in which we will allow RCAC to stabilize at a higher point of a coil, and then we'll bring the coil back to the point of easier oscillation. We will stop adaptation, and then we will disable the controller to allow the oscillations to form up. We'll enable the controller with an adaptation disabled, and we will show that the controller obtained in the previous position will not work on this new position due to different operating conditions. Then we'll allow adaptation to start once again, and we'll see how RCAC can readapt its controller coefficients in order to once again yield a set of controller coefficients that suppress the oscillations. So you can see initially, RCAC converged to a set of theta coefficients that were able to suppress the oscillations when the coil was placed at a higher position. But the same set of coefficients would not work with the original sound pressure signals at a lower position of greater oscillation. However, once we allowed RCAC to adapt its gains, it reached to a new set of parameters that were able to suppress the oscillations. This shows the capability of RCAC to readapt to new operating conditions. And that concludes our experimental demonstration. Please, if you have any questions, now please speak up. Or type them in the chat. Or speak here as well.
Do you always use the same number of coefficients?
Like I said in the previous presentation, I chose the number of coefficients because one of the at that sampling rate, I covered most of the waveform. And in all of these tests, I have used the same number of coefficients.
Would you expect the performance to be diminished if you use like fewer coefficients?
Yes. That being said, increasing the number of coefficients usually has no bearing on performance. The only issue is that it also increases the amount of computational effort that your computer needs to do. So if you increase the control coefficients too much, you may delay. You may not be able to run it as fast as you can.
Sure.
Okay, if no further questions. Yeah. If no further questions are required, then I'll stop the recording. Anyways, thank you for coming. And I hope you have a nice rest of your day.